Yep. All right. Let's go over those homework questions. So question one, we had dy dx equals y over x. That is a differential equation, a first order differential equation. In order to solve, right, it was asked that you solve for the general solution y equals f of x. In order to do that, we use the only technique that you're ever going to be taught or need to know in this class, which is separation of variables. So you have to get your y's on one side and your x's on the other. So how am I going to do that? Remember, these things dictate what goes where. So your dy here, right, is in the numerator. That means all your y's have to go to the left side. So then this is good where it is. You're like, well, what do I do with this y? Well, you can divide both sides by y, or think of it as multiplying by 1 over y. So if I multiply by 1 over y, I actually take my time here, rewrite what I have. I have dy over y dx equals, the y's here cancel, 1 over x, right? So now what about this dx? It's no good down there. So how do I get that up top? I have to multiply both sides by dx. And so they'll cancel here. And then when I rewrite it, I'm going to get dy over y equals dx over x. You don't need to piecemeal it and do it in two steps like this. You don't even need to show the work, quite honestly. You should be able to look at this and say, oh, divide both sides by y, get that. Multiply both sides by dx, get that. All right, but that's there just for note flavor. All right, so now why is this good? Well, it's good for a couple of reasons. One, my dy's and my dx's are up top, and that needs to happen. And the other is that they're connected with multiplication. And I know it looks like the division, but we can rewrite this as 1 over y times dy equals 1 over x times the x. So that means they're basically Riemann integrable, right? So that's the green light to integrate the left side, integrate the right side. Integral the left side, right? You know, function whose derivative is 1 over y. You know that. It's ln absolute value of y. Function whose derivative is 1 over x is ln absolute value of x. Technically, we should adding plus c to both sides. It's an indefinite integral. But remember, we learned the trick that, listen, you can add to both sides, but eventually you're going to subtract it over to another side. So what side do we really want it on? And we want it on this side because we're being asked to solve for y. Okay? So now what's our next move here? And this is where it gets a little funky because basically calculus is over. This is pre-calc world. I'm going to exponentiate both sides. So I'm going to e to the left side, and I'm going to e to the entire right side. So I end up getting that, right? E to the ln of absolute value of y is just absolute value of y. These guys undo each other. They're what's it called? Inverse functions. If there was something here in front of that log being multiplied, you'd have to remove it before you, so to speak, canceled by using a log property and bringing it up here. But there's nothing there, so we're good to go. But understand that that's probably going to happen in the future. And so now this was, remember the little trick that we can do here. Using your 7th grade property of exponents, you can rewrite this way, right? Because when you multiply two terms with the same base, you add the exponent. So this is certainly equivalent to that. And the whole reason is because now you have times some constant, right? But I'm going to change that e to the c and say, listen, you really could represent any constant k. And now what's the point of that? Well, the point of that is, well, then I can lose the absolute value bars, because I can make k positive or negative depending on what my initial value is, right? So I'll end up losing that. So this is it, done, solved for y. Put a happy cloud around it. What is it? It's an explicit general solution. It's a general solution because it's a family of functions differing by a constant k that satisfies this differential equation. It's explicit because we got y strictly in terms of x, right? That won't always be possible, but it was possible here, so we're happy. All right, let's go to the next problem that I asked you to do. So you had radical 1 plus x squared over 1 plus y times dy dx, and it equaled negative x. So it looks like my y is going to have to go to the left side because my dy is upstairs, and I like that. All right, so then if I'm looking at that stuff, think about this now, right? These are good because they're on this side. So I'm just going to write dy over 1 plus y. I'm not going to show all that sloppy work of multiplying both sides by whatever, right? I'm just going to get after it. And now These guys, not so good because this needs to get, it's a little thicker than I wanted there. This needs to get on, let's see, can I change the thickness? Let's do that real quick. Change you. All right, perfect. All right, hit that. This needs to get on that side along with that. So I would multiply both sides by dx. And then how would I move this? I'd have to divide both sides by that. So I would get negative x over radical 1 plus x squared dx. Now, again, I didn't show the work this time like I did on the last one. I don't necessarily think you need to do that. But if you do, do it. Okay? All right, so let's rock and roll now. So now we have both sides in a Riemann integrable form, right? This is like 1 over 1 plus y times dy. There's the times. You need that. If this would have been a plus, your whole day would have been ruined. And this is negative x over radical 1 plus x squared times the x. So we have the green light to integrate both the left and the right side. And this one's going to be a little bit more involved. So the integral of the left side, right? Back in the day, you'd let u equal 1 plus y, but you're like, oh, wait a minute, right? This is a linear u right here. So I can view this as 1 over stuff. So a function whose derivative is 1 over stuff is ln absolute value of stuff times 1 over the derivative of stuff. Well, the derivative of 1 plus y, right? It's 1 plus 1y. The derivative of that is just 1. So again, we're getting lucky with this 1 plus y stuff that we've seen a couple of times in the problems I've given you. Clearly, it's not always that. Okay, so there's your answer right there for that integral. And so now you come over here, and this is like, what do I do with that, right? So there's nothing linear about this, right? So how would you do this integral? Yes, you have to remember the stuff that you learned back in the day, which is a u sub. All right, so what would you let u equal? All right, it's a fraction, so you're thinking denominator, but there's a radical there. So the move there is to let u equal what's in the under the radical. So I'm going to kind of do this work to the side. So I'm going to say, hey, let's let u equal 1 plus x squared. So du is going to be 2x dx, which is sort of cool because I see x dx, but I don't see 2. But again, we know the deal. That's not a big deal. 1/2 du equals x dx. So that is actually pretty good. So this stuff here now, if I'm writing this over here, I have the integral. There's a negative. This x dx is a half du. And then this isn't u, it's radical u. Spruce this up a little bit, pull out the negative a half, and you get this. Liam, is that ln? Very good. It is not. It is only ln when it's du over u. And this is du over radical u. So you're like, well, what do I do? Well, you have to rewrite that, right? So you're going to use negative exponents. So it'd be u to the, hit pause and see if you know what the power is. I'm waiting, hit pause. Hit pause. Okay. Yes, negative a half. So now why is it negative a half? Negative because it's in the denominator, half because it's a radical. Two separate ideas. So realize we haven't integrated anything yet. We just did a u sub, we rewrote, and we simplified. Now it's time to integrate. So you have negative a half, and maybe I'll do the integral in red, right? Use the power rule here. Add 1 to the new power. So add 2 over 2 to that, you get u to the 1 over 2. Divide by that new power is like dividing by half, is like multiplying by 2. That's what you get. And then, of course, you get your plus c. Okay? So now, if I come back over here, think about what I have now. I'm not going to write the u here. First off, negative a half times 2, that's just 1. But I'm not going to write u to the 1/2 over here because u is this. So I'm going to write 1 plus x squared. That's the u to the 1/2 and then plus c. And if I wanted to, I can even write that as radical. Okay, so there you go. So we're rocking and rolling. Now, if we can solve for y, we should. And let's see if we can. So the only way that we can possibly do it would be to exponentiate both sides here. So we're going to e to the left side, and then we're going to e to the right side, entire right side. And then it's the same trick as before. So we're going to have to go to the big screen on this one. All right, cross you out. Extendomatic. All right, so here we go. So you're going to get, when you do this, e to the ln, they just undo each other. That was the whole point. So you get absolute value of 1 plus y equals, and then 7th grade exponent rule. This would be e to the 1 plus x squared to the half times e to the c. Multiply two things with the same base, add the exponents, that's what you'd get. And then you're like, oh, that's right, e to the c, you're just the constant. We'll call you k. This will be e to the, and you know what? Let's get fancy schmancy and call this radical 1 plus x squared. And since k can be positive or negative, I can lose the absolute value bars. And now to solve for y, it's pretty easy. Just subtract 1 from both sides. So I get y equals k e to the radical 1 plus x squared minus 1. Put a happy cloud around it. All right, what is that? That is your explicit general, it says general, solution. So in other words, this is a family of functions differing by a constant such that if I was to throw that into this differential equation, it would check. So in other words, put that y in here, put that derivative in here, multiply and divide all this out, the left side would boil down to negative x. If you don't believe me, do it, knock yourself out. I am not going to do it. All right, let's move on to the last homework question, which was dy dx equals 1 plus y squared. Oh, this is going to be a good one. Times 1 plus y squared times x squared. All right, so same deal. All right, maybe I won't use the colors here, and let's see if we can do it. Separate the variables. This dy says, hey, everyone's got to come over here. That's a y. Since this is connected with times, just divide both sides by 1 plus y squared. So I get dy over 1 plus y squared. All right, move this guy by multiplying both sides by dx. And look at that. Variables separated, both connected with multiplication, right? This is 1 over 1 plus y squared times dy, and this is x squared times dx. It needs to be times the d whatever, all right, because it needs to be Riemann integrable, which it is. So let's start with this guy first. So integral of x squared is going to be 1/3 x cubed, and we're going to add our constant only to this side, and then you go to this, and you're like, what do I do with that? Maybe you're thinking u sub. Maybe you're thinking that shortcut we did. Can't be the shortcut. All right. Does anyone know why? Pause the video. See if you know why. You back? All right. Can't do it because this is not linear. 1 plus y squared. So it actually wouldn't be a bad idea to think to do a u sub and let u equal 1 plus y squared. But the only way that would really work is if there was what in the numerator. Pause the video. Think about it. What needs to be in the numerator for this to be 1 plus y squared, if the u is going to be 1 plus y squared? If you answered y, then you are getting it. If you answered nothing, then I don't know. I don't know what to tell you. Anyway, so then what do you do? So it goes back to, whoa, wait a minute. Maybe I got smacked in the face when I saw this. In other words, do you know a function whose derivative is 1 over 1 plus y squared? And the answer is you do. It is your good friend arctangent of y. The derivative of arctangent of y with respect to y would be 1 over 1 plus y squared. So that is howdy doody time. So now that's good stuff. And the question is, can you solve for y? And you can. How do you get rid of arctan? All right. What do we think? Marco, what do you think? How do I get rid of arctan? Okay, good job. Yes, imply the tangent to both sides. So in other words, do the tangent of the left side because the tangent of the arctangent, they undo each other, you just get y. And on this side, you would get the tangent of all of this. Can't do it individually. You got to do the tangent of the entire thing, right? If you're not following that, I think you should be, but if you're not, listen, you want to get rid of this, you tangent it. Tangent of arctan of y for the appropriate y values is y, all right? And then you have to tangent this entire side. There's a little more to the story here, but for now, that's all we really care about. So this is it. So what is this guy? This is your, you guessed it, explicit. You know why it's called explicit? Because you solved for y. General, do you know why it's called general? Because there's a constant in it. Solution. So in other words, this is a family of functions differing by a constant such that it would satisfy this differential equation if you checked. All right. So hopefully you're rocking and rolling with these assignments and my dog is not annoying you too much. Peace out, Cub Scout.